recording. So for fluid flow, you've got current flowing, and the current is defined as how much volume per second, how much volume flows past that point per second. And what has to be different about these 2 points to make current flow in the first place? What's pushing that flow forward?
Velocity?
Velocity is related to current in that they're both derivatives with respect to time. But velocity velocity is distance over time. So they're related. But yeah, it's the pressure that's causing that flow in the first place. The fluid is flowing because there's a difference in pressure, assuming there's no other changes, assuming no change in height, no change in cross-sectional area. Presumably fluid is flowing from what pressure to what pressure?
High to low?
Yeah. We generally, all other things being equal, we generally assume fluid to flow from the high pressure zone to the low pressure zone. And what equation relates those together?
Bernoulli's equation?
Right. We can write out Bernoulli's equation, which in this case would be the version that's just delta pressure, nothing else is changing, equals, there's no pump, we just have negative IR, where R is the resistance of the pipe. The whole pipe has this property called resistance that represents how difficult it is for fluid to flow. So the difference in pressure causes current to flow, or to put it another way, the fact that current is flowing causes a difference in pressure. Resistance is the constant of proportionality, representing how difficult it is to make current flow through that pipe. And then the negative sign is really just representing direction. Negative sign means the current is flowing in the direction of decreasing pressure. Any questions on the fluid flow case so far? So let's transition to talking about electricity. We've got the fluid flow case versus the electrical flow. What's the electrical version of a pipe?
A wire?
Yeah, so let's say we've got a wire, which we usually just draw as a straight line, regardless of what shape the wire actually is. We often draw this with dots on both sides. The solid dot here means this might be connected to something else in the circuit, but we're just not going to draw the rest of the circuit. Also, if it's just wire is extremely easy to flow through. Usually we're not talking about just wire though, we're talking about a resistor, usually drawn as a zigzag. This doesn't mean the wire is actually shaped like a zigzag, it's just the symbol for this wire has resistance, or this thing has resistance. So that's similar, it's not the same exact meaning as resistance for a pipe, because we're talking about a different scenario, but it's going to serve the same role in the equation. And let's say we've got electrical current flowing through this wire with resistance. We're going to be defining current differently though. For electrical current, we're still going to define it as a rate of change with respect to time, but not about volume, because what's actually flowing in a wire?
Current? Wait, no.
Well, what is
electrons, right?
Yeah, we've got electrons moving around, right? We've got electrons moving through this wire, and we wouldn't want to have to try measuring the volume of individual electrons. And we also don't really want to count the electrons. We don't want to say how many electrons are going through the wire, because that's going to be absurdly large numbers. Instead, what could we measure about the electrons that describes another idea of how many there are? What's a property that every electron has?
Charge.
Charge. So we're going to define current for electricity. Electrical current is change in charge over change in time. That is how much charge flows past that point per second. And we usually write charge as a Q, sometimes capital, sometimes lowercase, depending on context. But current for electrical systems is defined as charge over time. And let's take a look at the units for that also. Anyone know what charge is measured in?
Isn't it amps?
Amps is going to be for the current.
Oh, charge is coulombs.
Yeah. Charge is measured in coulombs, written as a capital C. And then time, as usual, is going to be measured in
Seconds.
seconds, yeah. So coulombs is a measure of charge. It's a measure of how much electrical stuff there is. And it's difficult to really say what charge is. Charge is just a property that certain subatomic particles have. Every electron has a very consistent, identical amount of charge. Every proton has an identical amount of charge. So charge, we're basically using charge as an indirect measure of how many electrons are flowing past that point per second. But you can think of charge as serving the same role in the electrical equations that volume did in the fluid equations. Volume is how much fluid is flowing past that point. Charge is how much electricity is flowing past that point. And then current is the rate at which charge is flowing, how much charge per second. Whereas for fluid flow, current was how much volume per second. Same idea, we're just rewriting volume as charge. Any questions on that so far? And then for fluid flow, we were expecting that the current was flowing because there's a difference in pressure. Fluid's flowing from the high pressure zone towards the low pressure zone. What's the electrical version of that? What's the electrical thing whose difference is forcing current to flow? What would you have to attach to this, presumably, to make current flow?
Battery.
Presumably a battery, yeah. And the battery provides a difference in
Energy.
It is providing energy, but we wouldn't really talk about this in terms of a difference in energy from one point to another. In the same way that for fluid flow, the pump does provide energy, but we weren't talking about this in terms of high energy and low energy. We were talking about energy density. So if we look at this idea of energy density, for fluid flow, energy density was being defined as energy over volume. We were measuring the kinetic energy per unit of volume, the potential energy per unit of volume, and even pressure counts as energy per volume. So those are all energy densities. For electrical flow, though, again, we're not describing this in terms of volume. We're describing this in terms of what? How do we describe how much electricity? What are we using instead of volume in these equations?
Is it charge?
Yeah, we're using charge. So energy density for electrical systems is defined not as energy per unit of volume, but energy per unit of charge. This is also called the electrical potential. And it is also known as voltage. So we write that as a capital V. So voltage is energy per unit of charge. And this is going to serve essentially the same role that pressure did for fluid flow. For fluid flow, pressure was a measure of energy per unit of volume, and a difference in pressure forces current to flow. For electricity, voltage is energy density, but it's specifically energy per unit of charge, and a difference in voltage causes current to flow. So every point in the electrical circuit, every point on the wire has a certain value of voltage, a certain energy density. So voltage is basically a measure of how concentrated the energy is. High voltage means each electron has lots of energy. Low voltage means each electron has only a little bit of energy. And 0 volts would mean each electron has no energy. So if you got a difference in voltage, specifically if you got high voltage on one side of the wire with resistance, so high voltage on one side of the resistor, and low voltage on the other side of the resistor, that difference in voltage is going to cause current to flow through the resistor, and it's specifically going to be flowing from the high voltage zone towards the low voltage zone. So this is following exactly the same pattern as fluid flow. A difference in pressure across a pipe causes fluid current to flow from high pressure to low pressure. Likewise, a difference in voltage across a wire with resistance causes electrical current to flow from the high voltage zone towards the low voltage zone, in spite of the fact that the resistor has this property called resistance, the difficulty level. Any questions on that so far? And if we take a closer look at the units of measurement here for the voltage, energy density, voltage, electric potential, they all mean the same thing. If we take a look at this voltage here, so voltage equals energy per unit of charge. What are the usual units for energy and for charge?
Joules and coulombs.
Yeah, energy is measured in joules, charge is measured in coulombs, and the voltage is measured in units that we just call volts. So it's a little bit confusing, and sometimes that we use V for both the variable and the unit of measurement, but it's usually going to be at least somewhat clear from context that this V as a variable represents the voltage. V as a unit of measurement represents how many volts, the unit of measurement for voltage. So a battery might be marked 9V. That means its voltage is 9 volts. And a battery typically provides a boost in voltage in the same way that a pump in a fluid system provides a constant boost in pressure. In an electrical system, a battery provides a constant boost in voltage. If that battery says 9 volts, that means the two terminals have different voltages, and the difference in voltage is 9 volts. The plus terminal is 9 volts higher voltage than the minus terminal. Any questions on that so far? So we've got...
sorry, so like a 9-volt battery, that means the delta V is 9?
Yeah, delta voltage would be 9 volts. The voltage rating listed on a battery, 9 volts for a 9-volt battery, and I think typically 1.5 volts for the smaller standard batteries, the AA, AAA, I think even C and D cells. I think those are all 1.5 volts.
Okay, thank you.
So yeah, the units, volts is just an energy density, how much energy per unit of charge, and that's in joules per coulomb. For instance, that 9-volt battery, a 9-volt battery means that battery gives 9 joules of energy to each coulomb of electrons that flow through it. And then current is measured in amps, which just means how many coulombs of charge pass by that point per second. So 5 amps of current means 5 coulombs of electrons flow past that point every second. And these are related by an equation almost identical to the Bernoulli equation. Exact same structure. It's just that instead of pressure, what's the electrical version of pressure?
Potential?
Yeah, the potential, also known as the voltage. So we're going to have a delta potential or delta voltage. And both terms are used here. I think the formal term is electrical potential. It's often called voltage because it's measured in volts. So delta voltage or delta electrical potential, that is the difference from one side to the other, equals the same negative IR we have over here. And when I say the same, I just mean the same structure. This I is not the same as this I. This is charge per second. This is volume per second. And this R is not the same as this R. This is fluid flow resistance versus electrical resistance. They're very different units of measurement, but they serve the same role in the equation. In both cases, we've got the something is flowing because there's some difference in a variable that we think of as push, in spite of this level of difficulty called R. So these are the exact same sort of behavior, even though they're describing completely different physical phenomena. And because there's such similar behavior, for many years, it was thought that electricity was a form of fluid. If you look back at old textbooks from the 1800s, they describe electricity as a form of fluid. There's this mysterious thing that they call the electrical quantity or electrical fluid that's imagined as flowing through the wires. And by modern standards, that kind of seems ridiculous. We now know that it's these tiny particles called electrons. But from the perspective of not already knowing about atomic theory, it makes total sense that to think that electricity is a form of fluid because it has identical behavior in terms of the circuits. Any questions on that so far? And one more bit of terminology here. We've got the Bernoulli equation, or a simplified Bernoulli equation governing fluid flow. The equivalent for electrical flow is usually called Ohm's Law. So Ohm's Law is the idea that current through a resistor is proportional to the voltage difference. R is the constant of proportionality, the resistance of that object, and the negative sign just represents direction. We could also take a closer look at the units here, because we've got voltage is measured in volts. Current is measured in amps. So what does resistance have to be to make this work out? What fraction would convert amps to volts? We want to cancel out amps, right? So we could just put amps in the denominator, but we want to introduce what unit of measurement? Yeah, if we just have volts over amps, amps cancels out, we get volts. So resistance is measured in volts over amps, which is also called ohms. This guy Ohm got both the equation and the unit of measurement named after him. And ohms is typically written as the Greek letter capital omega. So omega, or ohms, is the way, so you'd read this as ohms. The variable used is omega, or the letter used is omega. 1 ohm is the unit of resistance. And 1 ohm is basically a resistor that will allow 1 amp of current to pass through if there's 1 volt of voltage. But ohm literally just means volts over amp. It's just an abbreviation for that. So anytime you see volts over amps, you can replace it with ohms. Anytime you see ohms, you can replace it with volts over amps. And likewise, anytime you see amps times ohms, you can immediately replace that with volts because the amps cancel out. Any other questions on that so far? And that page I linked on math.ncheese.org also has all of the information about the units as well, if you want to use that as a reference. All right, so resistors always have a delta voltage that's proportional to current with resistance as the constant of proportionality. So this is specifically the delta voltage for a resistor. If we look at other things that might be in a circuit, such as a battery, they're going to have different formulas for voltage. So all these voltages, we've got delta V for a resistor is always going to be negative IR. But what else might you find in a circuit? What other things might you use to put together a circuit?
Battery.
Yeah, a battery. And what does a battery do to the voltage?
We said it increases the voltage.
Yeah, the battery just provides an increase to the voltage. If you've got a battery, and in the circuit diagram, that's usually drawn as just a short bar and a long bar. Or sometimes a sequence of several short bars and long bars in pairs. So something like this. In the original notation, like 120 years ago, this would mean 2 batteries combined together. But most modern batteries are actually several smaller batteries combined together in one case. So this is usually just used to represent a battery or a cluster of batteries. And typically the long bar represents the positive terminal and the short bar represents the negative terminal. That is high voltage and low voltage. So this battery, in the same way that a pump in a fluid system, the push of the pump just creates a difference between a high pressure zone in the area that the pump is pushing on and a low pressure zone in the region the pump is pulling from. Same idea with a battery. The battery creates a difference between a high voltage zone and a low voltage zone. And that's ultimately due to a chemical reaction going on inside the battery. The battery contains chemicals, fairly unstable chemicals in a high energy state. These chemicals are slowly combining with each other to lower their chemical energy and release that energy as electrical current. Specifically, the chemical reaction causes a voltage difference, creates high voltage on one side, low voltage on the other. But the important thing is the battery is providing a constant amount of voltage difference. It's usually written as plus epsilon. So this epsilon here just represents the voltage provided by the battery, also sometimes called electromotive force. So electromotive force is just an older terminology for the voltage provided by the battery, the plus epsilon. And the important thing is that's a constant. No matter how much current is flowing through, like if there's different amounts of current, the delta V for the resistor will change. But different amounts of current does not change the voltage of the battery. The voltage of the battery is this constant plus epsilon no matter what. And that may diminish as the battery ages. Like if the battery wearing out, if you measure a worn out battery's voltage, it's going to be less than what's listed on the side of the box. But for the periods of time we're talking about in the experiments in this class, we're going to assume the battery maintains a constant voltage the whole time. And one other element, if you've got batteries and resistors, what do you use to connect them together?
Wires.
Yeah, just wires, which is generally just drawn as straight lines on the circuit diagram. And that's regardless of what shape they actually are. The actual wires might be curving or bent or whatever shape you want, but we usually draw them as straight lines. And the important thing about a wire, let's say you've got a certain voltage on one side. How much resistance do we assume a wire has?
None or negligible.
Yeah, we assume no resistance. Physically, any wire does have some resistance, but we deliberately make wires out of material that has very low resistivity. So we generally assume a wire has no resistance. The only exception to that would be like if you take a battery and connect the terminals with just wire. You have to assume the wire has some resistance there. It's just going to be a very small amount of resistance. But if there's any other resistors in the system, the wire has extremely low resistance compared to the other resistors. So we generally treat the wire as having 0 delta voltage. Delta voltage for just wire is going to be 0. In other words, you've got some voltage on one side, and then on the other side you have the same voltage. Any 2 points that are connected by just wire have to be at the same voltage. Even if it's kind of a long winding path, if you have any 2 points, if you can draw a path from one point to the other through just wire, going through no batteries and no resistors, those 2 points must be at the same voltage. So that's a very useful thing to look for. Anytime you've got some complicated circuit diagram and you're comparing 2 points, before you do anything else, ask yourself, can you draw a path from one point to the other that goes through just wire and nothing else? If so, then you know those 2 points must be at the same voltage. Any questions on those voltages so far?
If you have 2 batteries and they have different voltages, is their E just additive or?
Yeah, as long as they're in series with each other.
What was that?
As long as they're in series with each other, like if you just
got, right, as opposed to parallel, okay.
Yeah, if you just got like this battery and this battery, let's say you've got like a epsilon 1 equals 3 volts, epsilon 2 equals 5 volts. You can treat this series of 2 batteries as equivalent to just one battery whose voltage is epsilon total equals 8 volts.
So this was like when we were figuring out the resistance, it's like the same sort of equation, like, because I remember it was like 1/4 if it's in parallel, right?
Yeah, if resistors are in series, they can also just be added together.
Okay.
So if you just got a resistor and another resistor in series, those are going to be like just one big resistor whose resistance is R1 plus R2. If they're in parallel instead of in series, it's going to be very different. But if they're in series, you can just add the resistances.
Okay, cool, thanks.
One other voltage you're going to be needing later, we're not going to get to capacitors for probably a few weeks, but capacitors are another circuit element we're going to see later on. So if you want to just make a complete list of all the delta V's you're going to need right now, delta voltage for a capacitor is negative Q over C. A capacitor is basically two metal plates that are separated by a short distance, and those metal plates can store charge. So as charge flows, the plates build up more and more charge. And the capacitor pushes back with its own voltage, and the pushback, that's why there's a negative, because it's a pushback. The pushback is proportional to how much charge is on the plates right now. And then C is a constant of proportionality called the capacitance of that capacitor. Again, we're not going to be using this for a few weeks, but if you want to make a complete list now, there's your complete list. These are all of the delta V formulas we're going to need in this class. There are other circuit elements that have other formulas, but they're beyond the scope of 7B. Any other questions on that so far? So let's try out an example. Let's see if we can actually analyze a circuit. And typically analyzing a circuit means finding all of the currents. In most cases, not all cases, but in most cases, we usually know the voltage of the batteries because those are labeled on the sides. We usually know the resistances of the resistors because those are usually also labeled. The current is usually what you're trying to find. That's not always the case. Maybe sometimes you know the currents because you can measure it with an amp meter, and there's some resistors you don't know, or maybe there's an unlabeled battery or something. But as long as you know enough information about these values, epsilon, I, and R, in the circuit, you can calculate the rest of them. For example, let's say we have a circuit consisting of a battery that is connected to a resistor here, and then a resistor here, but also this splits off and there's another resistor here. And let's say these are let's say say 2 ohms. And let's say 3 ohms and 4 ohms. And let's say this is a 52 volt battery. I think that'll work. So we know the voltage of the battery, we know each of these resistances, and what we're trying to find is the current. So what we want to do here is we want to start labeling every current that could possibly exist in this circuit. And I usually start with the battery. We've got current flowing through the battery. If the current flows through the battery, what's the very next thing the current's going to hit?
First resistor?
Yeah, the current's going to go through the first resistor. And what should we assume about the amount of current flowing through the battery and the amount of current flowing through that first resistor?
Well, didn't you say the amount of energy would be constant?
Well, the amount of voltage provided by the battery is constant. So this battery is providing a voltage of 52 volts all the time. So if we start labeling voltages, because every location in the circuit has a voltage associated with it. Typically, I usually start right before the battery and call that point 0 volts. You don't necessarily have to. There's nothing special about 0 here. It's just being used as a reference point. But let's say we call the point right before the battery 0 volts. We go through the battery and we consult our table of delta V's. Delta V for the battery is plus epsilon. If you go through the battery, that creates a difference of plus 52 volts. So we go from 0 volts to 52 volts. So this corner is a 52 volt location. But it's not just this corner, it's this entire region. So this entire zone is a 52 volt zone. And likewise, it's not just this point that's 0 volts. If you travel along wire, you get no change in voltage. So any point connected to this by just wire is at 0 volts. So this entire region, up until we hit the resistors, because as soon as you hit a resistor, the voltage can change. But this entire region is a 0 volt region. So this point is 0 volts, this point is 0 volts. This entire F-shaped region of wire is a 0 volt region. But as soon as you cross over a resistor, the voltage changes because a resistor has a delta voltage associated with it. And we don't know how much the voltage changes because we don't know the current through that resistor yet. But if you've got current flowing through the battery, that current has to continue along this path. So what should we assume about the current flowing through the battery and the current flowing through resistor 1?
It should be the same.
Yeah, those should be the same. This is exactly the same continuity principle we've been working with for fluid flow. If you've got a pipe, no matter how the pipe is shaped, as long as there's one path, the current everywhere in that pipe has to be the same. Current in must equal current out. The same is true for electrical flow. For any single point, like for this corner, the current flowing into this corner has to match the current flowing out of this corner. For electrical systems, that's usually called the junction rule. Or sometimes called Kirchhoff's voltage law, or sorry, Kirchhoff's current law. And that is just the statement that the current flowing into a point must match the current flowing out of a point. So, or more generally, the total of all, the sum of all the currents flowing in must equal the sum of all the currents flowing out. And this is true for any point on the wire. It's called the junction rule because it's usually most useful at a junction. For instance, if you've got a bundle of several wires meeting, let's say you've got like 6 wires meeting at a certain point, and you've got some current flowing in, let's say I1 and I2 are flowing in, but then I3, I4, I5, and I6 are flowing out. What would we assume about these 6 currents? How would those have to be related to each other? What's the total current flowing in to this point in the middle?
I1 and I2.
Yeah, I1 and I2 are both flowing in. So we could say the total current flowing in is I1 plus I2. And then everything else is flowing out. I3, I4, I5, and I6 are all currents flowing out. So we can say the sum of all the currents flowing into that point has to equal the sum of all the currents flowing out of that point. And this can often be very useful because if you know all but one of those currents, you can immediately calculate that last missing current. We can apply that at this junction, for instance. Let's say we call this current I1. the current flowing through the battery, and this first resistor. As soon as the current hits the junction though, in the same way that fluid flow hitting a junction is going to split, same thing for with electrical flow. Current 1 hits this junction and splits into, let's call this current 2 and current 3. So the current splits up, but we can use the junction rule here. The current flowing in is I1, the current flowing out is I2 and I3 together. So we can say for certain from the junction rule that I1 equals I2 plus I3. Which means, among other things, if we can find any two of those currents, we can immediately calculate the third one as well. Any questions on that so far? So we've got 3 unknown currents. And in general, if you've got 3 unknowns, you want to have 3 equations to work with. We've got one equation from the junction rule. The other equations we can get from what's called the loop rule. Or Kirchhoff's voltage law. And this has to do with what's going on in a loop. If you start at some location and travel along the wire in a loop and eventually get back to the starting point, what should you expect about your starting voltage and ending voltage?
It'll be 0.
Yeah, or at least the change would be 0. You might start and end at any voltage, but you're going to start and end at the same voltage as each other. So the total of all the changes is going to be 0. For any complete loop, as long as you're starting and ending at the same point, the sum of all of the delta voltages that you encounter in a complete loop has to add up to 0. And you may have some voltage boosts because of batteries, you may have some voltage drops because of resistors, but all those changes have to add up to 0. And that's true for any loop. That doesn't mean the whole circuit. That doesn't mean everything. That just means in a single loop, any path that starts and ends at the same point. For instance, if we start here and travel around this loop, we started and ended at the same point. Let's call that the left loop. So we're ignoring the right branch, I3. We're just looking at the left loop. As we go through the left loop, what things are changing voltage? Or what voltage differences do we encounter? Like if you just stand here and start walking, what's the first thing you encounter?
The first resistor?
Even before the resistor, what do you encounter?
The battery?
Yeah, you go through the battery. So there's a delta V associated with the battery. You then go through the first resistor. There's a delta V associated with that first resistor. And then you keep going, and what's the next thing you encounter?
Resistor 2?
Yeah, resistor 2. So delta V R2. And at that point, you get back to your starting point. So these changes have to add up to 0 because they form a complete loop. And note that resistor 3 is not part of that loop because this path did not take us through resistor 3 at all. We could then fill in our delta V formulas. Delta V for the battery is plus epsilon. Every resistor is just going to be a minus IR. In this case, specifically I1 times R1. And then for resistor 2, it's I2 times R2. So the current that's passing through that resistor times that resistance. And we could even fill in some values here. We know the voltage for the battery is 52. And I'm going to leave off the units here and just treat this as numbers. Minus resistor 1 is 2 ohms, so 2 times I1. And then resistor 2 was 3 ohms, so 3 times I2. Or we could even just add these terms to the other side and get 2I1 plus 3I2 equals 52. So that's a fact we now know about current 1 and current 2 and how they're related to each other. We can't really solve that yet because this is one equation with 2 unknowns, but this at least tells us how I1 and I2 are related to each other from the left loop. Any questions on that so far?
I have a question.
Mm-hmm.
I thought that current remained constant, so why are there 2 different variables?
Current is going to be the same throughout any single path, but as soon as you hit a junction, like the current's traveling along this path, the current hits this junction and splits. The current is basically just telling you how many or how much charge per second, which you can interpret as a different way of measuring how many electrons per second. So a certain number of electrons enter this point per second. The same number of electrons have to leave per second, but some of them go this way and some of them go this way. So the current is going to split up when it hits a junction like that.
Oh, okay. Thank you.
Mm-hmm. Now, if there was only one loop, if this path wasn't there at all, if there's truly just one loop in the whole circuit, then there's just one current everywhere. But the fact that we've got this branching junction means that the current splits up. If we want more information, we're going to need to make another loop. So let's say we set up a different loop around, let's say we just start here and go through the outer loop, go around the outside of the circuit. In that path, we're encountering the battery, resistor 1, and resistor 3, but not resistor 2. So that's going to look like delta V for the battery plus delta V for resistor 1. We're not going through a resistor 2, but we are going through resistor 3. Then we get back to the starting point, so those have to add up to 0. If we fill in the values, delta V for the battery is still 52 volts. Any resistor is going to have delta V equal to negative IR. So for resistor 1, that's negative I1 times 2. And for resistor 3, we got I3 times 4. So there's our loop rule equation for the outer loop. And again, we could add these negatives to both sides and get 52 equals 2I1 plus 4I3. And now we actually have 3 equations, 3 unknowns. We know 2I1 plus 4I3 equals 52. We know 2I1 plus 3I2 equals 52. And we also know I1 equals I2 plus I3. That's a system of 3 equations, 3 unknowns, so that can be now solved using substitution or elimination or some combination of those. For example, everywhere you see I1, you can replace it with I2 plus I3. So in this equation and in this equation, replace I1 with I2 plus I3, and then you now have 2 equations with just I2 and I3. And then you can use substitution or elimination to solve for I2 and I3, plug those back into here to find I1, and then you know the current everywhere. So that's one way to analyze a circuit. Use the loop rule and junction rule, these laws here, to create a system of equations with the currents presumably as the unknowns, and solve that system of equations using substitution and elimination. Any questions on that? All right, so try solving that system of equations yourself to get some practice and see if the currents you get end up making these equations true. If you want some more practice on circuits in general, I've got a worksheet on, if you go to math.ncheese.org/P7C, there should be a circuits worksheet. And we'll look into some more examples of this in workshop next time as well. Feel free to email me if you have any other questions, and I will see you next week.
Thank
Hello.
you.
You're welcome.
Thank you.